We know that there are 90 naturally occurring elements. If you look on your periodic table, the last naturally occurring element is uranium with an elemental symbol. I think I put a UUU in there. Let me spell that correctly. Uranium, the last naturally occurring element, which is number, you can see it on the periodic table at the element U, it's number 92. And so since there are naturally occurring elements in the terms of 90, why is uranium number 92? Well, the heart of that answer lies that there's 2 synthetic elements found in the previous 90 elements. And so as we go through and discover some unique properties, you'll soon realize that number 43, for instance, is a naturally, an element you won't trip over in nature. It's been produced in a lab. So about 90 at this point. An element is a pure substance that cannot be broken down into simpler substances by a chemical reaction. We know that each element is identified by a 1 or 2 letter symbol. Each first letter must be capitalized. For instance, if I have an elemental symbol for carbon in its 1 letter, it must be a capital C. If I have a 1-letter symbol and it's for potassium, it must be a capital letter K for potassium. And if the elemental symbol has a 2nd letter, it must be lowercase, must be. And let's take an example there. The elemental symbol for cobalt is C(o). The elemental symbol for copper, C(u). And the reason that's important, let's take an example of writing CO that are both capitals. That's actually representing 2 separate elements. Capital C is the element carbon. Capital O is the element oxygen. C(o) we said was the element cobalt. Therefore, we can see the importance of making sure we follow the rule of higher case, lower case. If we look at Cu, we have the element carbon, but capital U is uranium. Cu is the element copper. So we're stressing that it's important to follow the rule about 2 symbols, 2-lettered symbols having a first letter that's capital and a 2nd letter that's lowercase. And we know that elements are arranged according to the number of valence electrons on the periodic table. And that's our journey, is trying to explore where the elements are located, and where they're located gives us insight into their chemical properties. Much about the position of an element lies with where it lives on the table. So let's take some time, and I want you to just practice learning some elemental symbols. You have a periodic table in front of you, and you have a chart to fill in. I'm going to ask that you pause the video and spend some quality time using that periodic table to become familiar with what I would say the most common elements. And underneath that, there's a second chart, and I want you to fill in some unusual elemental symbols. This will take you a bit of time, so be sure you pause the video. Do not cheat yourself of the practice. Start looking up the elements. Let's begin. Well, welcome back. So you have your periodic table. You've been spending a great deal of time going through and finding each element. For example, the first element is bromine. You found that as number 35 on the periodic table. It has a capital R, capital B, lowercase r, bromine. Calcium you found on the periodic table, you found it as number 20, Ca. Carbon you found on the periodic table is number 6, capital C. Chlorine was number 17, that's Cl, lowercase. Chromium number 24, Cr. Cobalt number 27 gives us C(o). Copper, who is number 29, is Cu. Fluorine, number 9, is capital F. Hydrogen, number 1, is capital H. Iodine, number 53, capital I. Lead. If you find lead on the periodic table, you'll see it's number 82, Pb. The element magnesium is number 12. You found Mg. Manganese is number 25. You found that as Mn. Molybdenum. Now that's a fun word to say, isn't it? Molybdenum is number 42, Mo. Nitrogen is number 7, capital N. Oxygen lives right next door at number 8 as a capital O. Phosphorus, number 15, is capital P. Potassium, number 19, is the letter K. Sodium, which you find as number 11, you wrote as Na. Sulfur. Sulfur has the number 16, capital S. And number 30 is the element zinc, written as Zn. How many did you know by heart? How many did you have to really search for? Again, you'll always have access to a periodic table, but I want you to keep practicing and just kind of work for speed. And the speedier you become, the more proficient you become. And so there we can see our symbols for the elements when given their names. And I asked you to challenge yourself in filling out what we called kind of unusual elements. The first one was antimony. Did you find it? It was number 51. It's Sb. Gold is on the periodic table at number 79, Au. Lead we had filled out, number 82, Pb. Potassium, we're writing again, letter K. Sodium, number 11. Tungsten has absolutely nothing to do with the letter it comes from. Did you find it at 74? It's a capital W. The element copper, writing again, Cu. The element iron was at 26, Fe. Here's mercury. Mercury is number 80 at Hg. Silver was number 47, where you found it, with Ag. And the last one was tin. Tin has the number 50 and the elemental symbol of Sn. So with your periodic table, you found the names of the elements and their symbols. And we're just stressing that just takes practice, repetition, and you start to remember them. And if I say, don't worry about memorizing, eventually you end up memorizing because you look them up so often. So here's our periodic table. I provided you a copy. Now I did not copy this one because there's no names on the chart here. So each symbol is provided, but I went to the internet and found one that also gave you the names, just so you didn't have to worry about memorizing names versus symbols. They're provided for you on each quiz or test. But you can clearly see that we have a color coding system going on here that we should kind of think about. This periodic table is divided into 3 sections. We can see the first section, which is by far the largest, to be the metals. And they're coded in kind of that green shaded color. And they are noticeably to the left of that darkened staircase line. The second category is color coded in blue, and these are the nonmetals. And those tweener elements, the ones that lie between the metals and the nonmetals, are called metalloids. Sometimes you hear those called semimetals. Either word is absolutely correct. And let's investigate those one by one. And the first of those 3 groups we called metals. We said the 3 groups were metals, nonmetals, and metalloids. These metals are located to the left on the periodic table. By far, we have more naturally occurring metals than we do nonmetals and metalloids, the most abundant type of element. Some of their physical properties include being very good conductors of both heat and electricity. And if they've not been oxidized, which means tarnished, metals are very shiny at room temperature. Except for mercury, I'm going to say Hg for mercury, all metals are solids at room temperature, except for mercury, which happens to be a liquid. It's a silvery liquid. Can you think of a mercury thermometer where you have a silver liquid that goes up and down in the thermometer? We kind of outlaw those these days with mercury poisoning, but that silvery liquid is known as mercury. Those nonmetals are to the right of the periodic table, and they have their exact opposite qualities as the metals we just listed. If metals are shiny, the nonmetals are dull. If metals are great conductors, nonmetals are very poor conductors of both heat and electricity. We said that metals are solids at room temperature, except for mercury, one exception, but nonmetals can be in any form. Nonmetals can be in solid form, liquid form, or gaseous form. So, for example, elements that are nonmetals in the solid form at room temperature include both sulfur and carbon. Elements in the nonmetal form that are liquids at room temperature include bromine. And some gases, multiple examples here, but I chose to write nitrogen and oxygen, but there are many other gases as well. Did you know that there are only 2 liquid elements at room temperature? There's only 2. They are the element bromine, which is a nonmetal, and the element mercury, which is a metal. All other elements are either solids or gases at room temperature. These are the only 2 elements that you find in nature occurring as a liquid. And we mentioned that third category called metalloids, kind of the in-between, not quite a metal, not quite a nonmetal, but rather has qualities of both. These are located directly on the solid line that starts between boron and angles down like a staircase. And let me highlight that with you again. When we think about the metalloids, I put the crayon. I'm going to highlight in yellow what I call a staircase that separates the world of the metals to the left and the nonmetals to the right. You can see clearly that the metals shaded in green are far more abundant than the elements shaded in blue. But those that are shaded kind of in this tan color lie directly on the line and have qualities that both nonmetals and metals share. For example, the element silicon. This is a prime example of a metalloid. Silicon is a very excellent conductor. It is the base of all electrical conductors in computers, supercomputers. Silicon Valley is named after this element simply because of its fast computing speeds. And yet, it's very dull, just like other nonmetals are. It's not a shiny solid like metals. So you can see it has qualities of both. So metalloids, there are 7 of them that were shaded. The element boron, the element silicon, germanium, arsenic, antimony, tellurium, and astatine. We're writing those 7 elements that are considered to be metalloids by name and symbol. I'll repeat them to give you a chance to write. We have boron, capital B, silicon, Si, germanium, Ge, arsenic, arsenic and old lace, that's a poison, it's a white powder, As, antimony, Sb, tellurium, Te, and astatine, At. I'd like you to practice. Locate each element on the periodic table and decide if it's a metal, nonmetal, or metalloid. Please pause the video. Don't cheat yourself of the practice. Pause the video. Look them up on the chart and write metal, nonmetal, or metalloid. Come back when you're ready to check. Well, welcome back. I'd like to share answers with you. I have located each one of the elements and have decided based on its location if it falls under metal, nonmetal, or metalloid. Letter A, you found titanium at number 22. Titanium is shaded green. It's to the left on the periodic table. It's classified as a metal. Chlorine, you found at number 17, which lies in the heart of the nonmetal families. Krypton, you found at number 36. That indeed is also a nonmetal. Palladium, elemental symbol PD for palladium, you found that at 46. That's a metal. Arsenic, you found that at number 33. That is indeed one of the metalloids. Cesium is number 55, lies in the metals. Selenium, number 34. You can see selenium is a nonmetal. Osmium, number 76. Osmium is a metal. Little hunt and find until you get familiar with the location of the elements and can classify them based on their location as a metal, nonmetal, or metalloid. These building blocks we call elements. Of all of those elements we've been practicing, there truly are 4 key essential elements that compose the vast majority of the mass of the human body. That includes the element oxygen, the element carbon, the element hydrogen, and the element nitrogen. And of these, the vast majority contain carbon atoms. Carbon, hydrogen, and oxygen are found in these 4 main types of biological molecules. We call those the main biological molecules of proteins, carbohydrates, lipids, and nucleic acids. Proteins and nucleic acids contain nitrogen. All of these biological molecules will come out at the end of our semester, and we get to chapters 19 to 22. So thinking about the organization of our semester, chapters 11 through 18 focus on organic molecules. We will learn about organic molecules and their functional groups and the reactions they undergo. When we get to 19 to 22, we literally see the syllabus here. We start with proteins, carbohydrates, lipids, and nucleic acids, 1922, 122 in that order. So biological chemistry or biochemistry kind of wraps up our semester together. We have major minerals based on these elements that are present in our bodies as well. These elements are present in very small amounts. At least 100 milligrams of each are needed in our daily diet. For example, 2 elements that are considered major minerals would be magnesium with the elemental symbol Mg and the element sulfur with its symbol S. Both of these elements are key in the structure of proteins. And secondly, we have what are called trace minerals. These compounds are usually less than 15 milligrams required in our daily diet. Iodine is an example of a trace element. Iodine is needed for the proper function of your thyroid. Iodine follows the trend when I go, I jumped here. Fluorine, chlorine, bromine, iodine. Hear how I'm ending that? Although many of us call it iodine, which is absolutely fine to say as well. So we can see kind of a focus on the elements in the human body where the major building blocks, the 4 main elements, are oxygen, carbon, hydrogen, and nitrogen, composing really about 96% of the human body mass. You find major building blocks of muscle tissue in all 4 building blocks in terms of fats, which are called lipids, sugars, which are called carbohydrates, amino acids being the building blocks of proteins. Look at all the trace elements found in our body. There's quite a remarkable list here from arsenic, boron, chromium, and on down. And then major minerals are listed as well, such as potassium, sodium, chlorine, magnesium, and sulfur found in the muscle, and the calcium, phosphorus that are present in our teeth, giving us strength in our bones. Elements are pure matter. They are composed of a simple, single type of atom. We also discussed the term compounds in Chapter 1 as also being a form of pure matter, but the key here is that it's composed of two or more elements chemically bonded together. And that's key, is they're not just physically blended, sharing a container, but they are bonded together. A chemical formula consists of two parts. The chemical formula first gives us the elemental symbols, which are those one or two letter symbols representing names of compounds. So it's telling us what elements are present in the compound. And the second key is the subscript. It's going to show us how many of each element are present in the compound. These formulas do not give us insight into the connectivity of the atom, how atoms are put together, but it does tell us how many of each atom there are. So two examples might be water. When I read the chemical formula H2O, I can see that there are two atoms of hydrogen and one oxygen atom bound together to form one compound we call water. Here's an organic molecule called C3H8. C3H8 is a molecular formula that contains 3 atoms of carbon and 8 atoms of hydrogen. It is one substance, giving us a molecular formula for the compound we call propane. The way that we draw compounds, we'll see several different ways. This year, when I see just plain old water, we're getting a molecular tiny of each atom we have, 2 H's and an O. A ball and stick representation are using molecular models, kind of like Tinker Toys, if you will. These molecular models have different colors for each atom, and you connect them by a wooden stick to represent the bonds. So if I see a gray colored atom, I'm going to let that be represented by hydrogen. If I see a little bit larger atom colored red, we'll learn that this is denoting oxygen. You can see here, this is water in the gaseous phase. We call that steam because I can see no organization, clear random motion, very far spread apart. So I know that they're in the gaseous phase. And I can see what's called a space filling representation. Again, hydrogen connected to oxygen. All of these different colors in a molecular model kit represent specific atoms. In the molecular model kit, a black atom is representing carbon. Either white or gray represents hydrogen. Bright red is oxygen. Blue represents nitrogen. Yellow is the element fluorine. Green is chlorine. Kind of a darker red, bromine. Purple is iodine. Brighter yellow is sulfur, brighter than fluorine. And kind of an orange represents the element phosphorus. So we color code each of these, and if you printed your notepad in color, they came out. If you didn't print in color, perhaps you'd like to kind of jot in which each atom represents in color. And I say that because when you take your quiz or your test and are looking at molecular models, they'll be color coded. So let's practice. Practice identifying each element used in each example of the molecular art. So again, color coding. Do you remember that blue from the page represented the element nitrogen? The color red represented the element oxygen. So what do we have for each in terms of like the presence inside this circle? Right here, I have 2 nitrogens bonded together in a single compound. I represent that in the elemental symbol of nitrogen. Nitrogen, we know, will be a diatomic molecule. Now, what does that word mean? Diatomic molecule. Well, 2 atoms of the same element bonded together. A nitrogen bonded to another nitrogen is a molecule of nitrogen, but since they are both the same atom, it is still a pure element. Oxygen is bound to itself as well. A single molecule of oxygen is the elemental form. It is a diatomic molecule, two atoms of the same atom, same element bound together. And now all of a sudden I'm seeing two compounds, two units of a compound that is composed of a nitrogen colored blue and an oxygen color-coded red. This coefficient is telling me how many of those molecules I have. And the subscript, remember, tells you how many atoms. I'm writing that down for you. There we go. So, because I have two identical molecules, these are both the same, I have a coefficient of 2. There are two molecules of NO. Because the subscripts are both ones, now they're not there, but we know that if no subscript is present, it is indicating the number 1, that there's one atom of nitrogen bound to one atom of oxygen in a molecule called NO, nitrous oxide. So identify the elements. We had nitrogen and oxygen, and we had compounds, two of them in that circle, NO, N chemically bonded to O. Now, the elements bound in this molecular art, we know that this right here represents, when I see a black atom, represents the element carbon. When I see a white, or you can consider that gray, that these represent hydrogen. And the blue, I was writing blue, represents the element nitrogen. So put that together and we have one molecule, one because it's just everything's bound together. Structurally, we have a C bonded to 3 H's, carbon bound to nitrogen, coming out is 2 hydrogens, and because we know nitrogen needs 5 valence electrons, or soon will, we'll know there's an electron pair. So that's the direction we're heading, is being able to predict what elements there are based on the ball and stick model. Good work. So kind of going over that answer, the blue spheres we know were nitrogen. Blue represents nitrogen. The red spheres were oxygen. And when we had elements, they were the same colored atoms bound together. And when we had compounds, we had different colored balls bound together. This represented a single molecule containing carbon, nitrogen, and hydrogen. We had CH3, NH2, carbon and nitrogen bound together, completing their octets with hydrogens. Identify the elements in each chemical formula and give me the number of atoms of each. Now let me model using letter A, and then I'd like you to pause to complete that as you proceed. So NaCN is our first letter A example. What I'd like to see on your paper is Na standing for sodium. How many sodiums in that formula? Well, the subscript next to it is 1. Even though it's not written, if no subscript isn't present, you know it's a 1. C stands for the element carbon, and there's 1 of those. N stands for the element nitrogen. So this is kind of a sneaky way of getting you to practice names with symbols and counting how many of each. Pause the video and continue the work. Come back when you're ready to check. Okay, welcome back. We'll talk about H2S. H represents the element hydrogen. Whoops, I can talk and spell. Hydrogen. There is 1 hydrogen in that formula. Oh, Linda, there's 2 hydrogen in that formula right there. S represents the element sulfur, which this has just 1. Letter C, C2H6. C represents the element carbon. That subscript is 2. There are 2 carbon atoms in that molecule. H represents the element hydrogen. There are 6 atoms of hydrogen in that molecule. There are 8 atoms bound together. 2 carbons and 6 hydrogens gives me 8 total atoms in that compound. Letter D gives us the formula SnF2. Do you remember what Sn stands for? That's the element tin. Its subscript is 1. F stands for the element fluorine, Fluorine. I count 2 fluorines. CO gives us 1 carbon and 1 oxygen. And letter F, glycerol is how you say that. Glycerol, C3H8O3. We have 3 carbons, 8 hydrogens, and 3 oxygens. So practice really with the periodic table, kind of working to memorize names and symbols, or getting familiar with them, and letting us remember that subscripts tell us how many of each element are present in a compound. Good work. Let's talk about how atoms are put together, the basic structure of an atom. We know that atoms are the basic building block of all of matter, and that atoms are composed really of 3 subatomic particles. Those subatomic particles are known as the proton, the neutron, and the electron. There are 3 subatomic particles. The first of the 3 is called a proton. The second is called a neutron, and the third is called an electron. Of those 3 particles, the proton bears a charge of +1. A neutron bears no charge. It's called neutral. And an electron bears a charge of -1. Notice that the mass of a proton and a neutron are essentially the same, very similar to being the same. So the mass of a proton equivalent to the mass of a neutron. However, when you notice this particular mass, the mass of the electron is so significantly smaller than the mass of the proton or neutron, we refer to it as negligible. Here's my example. Let's suppose I have a very large German Shepherd, and I'm really trying to draw a German Shepherd. It's going to end up looking like a horse. I have a very large horse. That could be so many different animals. So a large mammal of some sort. You're getting the idea. I'm an excellent drawer. I take this large German Shepherd to the vet, and I have him stand on the scale, as usually you do when you arrive at the vet. And the scale reads 90 pounds for this beast of an animal. 90 pounds. It's a very large-sized German Shepherd, whatever it might be, Rottweiler, so many different choices. You know that I own Yorkies, so this is far beyond my realm. But now envision, on this horse is a tiny little flea. Does that flea have mass? Well, yes, a flea has mass, but in relation to the entire structure, would you agree that the scale would not change significantly, if at all, if a flea was present or absent on this large animal. That is the same idea with an electron. Electrons are so small compared to these large protons and neutrons that their mass is so negligible that we disregard it when we weigh an atom. So when we weigh an atom, the only two parts that will contribute to the weight will be found in the nucleus, the protons and neutrons. And electrons, which are lost, gained, or shared in the process of turning elements into compounds, really don't affect the mass overall at all. So they have a negligible mass compared to the larger particles of protons and neutrons. We know that protons and neutrons reside in a structure known as the nucleus. The nucleus is kind of the center of an atom where we find the protons and neutrons. It is the dense core of an atom. It's so small compared to the size of the electron cloud, yet it contains most of the atomic's mass, most of the atom's mass. So it's a very dense, meaning, massive area, but it's very small in relation to the overall size of the atom. The location of the electrons lie in the electron cloud outside of the nucleus. It comprises most of the atom's volume. But keep in mind, since electrons are so small compared to protons and neutrons, we consider it to be mostly empty space. So here you have this tiny little nucleus and the electron cloud residing outside of it. This volume, where the electrons reside, is quite massive, and yet mostly empty space. Not enough anything in there to contribute to the weight of the atom. We know a little basic law of electricity where opposite charges attract. We know that like charges repel. So in terms of a structure of an atom, two positive charges will repel each other. So a positive proton, when it becomes close to another positive proton in the nucleus, there's a repulsion. The electrons exhibit the same characteristic. One electron with its negative charge, if it becomes near another electron with its negative charge, they repel. And we know that opposites attract. A proton with its positive will attract the negative electron. Protons and electrons attract each other, whereas two like particles will repel. From the periodic table, we notice that there are numbers inside each elemental box. Now on the periodic table I printed for you, up high, let's say for example lithium, kind of in the top left corner, you see a whole number integer. These integers increase one by one as you read the chart left to right. Hydrogen 1, helium 2, lithium 3, beryllium 4, and so forth. What you are referring to is the atomic number of the element. Every element has a unique atomic number. It's unique because it is indicating the number of protons inside the nucleus. So just by seeing the number 3 in the box for lithium on the periodic table, we now know by the very definition of atomic number that it contains 3 protons in its nucleus. And every atom of a given element has the same number of protons. It gives the atom its identity. If I were to ask you, hey, what element has 6 protons inside of its nucleus? You would just simply find number 6 on the periodic table and say, well, the only element would be carbon with 6 protons in the nucleus. Because if I were to add one more proton, I've changed the identity and made it nitrogen. Different elements have different atomic numbers. Different elements have different proton numbers. And remember, since an atom is neutral, the number of positive charges must equal the number of negative charges so that it's neutral overall. So the number of protons must equal the number of electrons. Positive protons will match negative electrons in a neutral atom. They are electrically balanced, positives and negatives. The second number that we'll talk about here is called a mass number. The mass number is not found on the periodic table, and I'll explain in a moment when I compare it to a next term called atomic mass. This is a definition for mass number that refers to a very specific isotope of an atom. The mass number is defined as the total mass of an atom found by adding protons and neutrons in the nucleus. It's always a whole number. There's no such thing as a fraction of a proton or a decimal point of a neutron. Protons and electrons and neutrons are whole pieces of particles. You can't divide them any further. And so atomic number, number of protons and electrons, mass number is called protons plus neutrons. And now what we look at is a standard isotopic notation. The standard isotopic notation, I'm just kind of getting that ahead of us there, is on page 7. Let's say we have a general formula. Any element, let's just use a general symbol for X. Any element X, X represents any elemental symbol. Up high as a superscript, we are going to put its mass number. And the mass number you could see had a little symbol there. And the little symbol there was A for mass number. But I'm going to choose to write the words so you remember what they stand for. So I have the mass number written as a superscript up high. The mass number is defined as the weight of the nucleus. How many protons and neutrons? A very specific isotope. The mass number, protons and neutrons. The atomic number, of course, gives us the identity of the element, and that is a subscript to the left of the symbol. Alrighty, so here's 3 examples. The standard isotopic notation for the element lithium could be represented by Li, the elemental symbol, 7/3 to the left of the symbol. That tells me the mass number is 7. The elemental symbol in standard notation for sodium. The mass number would be 23 and the atomic number 11. 23/11. Notice the trend, big number over small number, big number over small number. A standard isotopic notation for carbon 12 places 12/6. Mass number over atomic number. Now, what kind of information can we gather from that? Notice that, let's just take this lithium 7/3. How many protons, how many neutrons, and how many electrons in that standard notation? We know all 3 of those components from those 2 numbers. Remember the very definition of atomic number? Atomic number tells me the identity of the element. The atomic number is 3. Therefore, I know with confidence there are 3 protons inside of the lithium nucleus. And because atoms are neutral, I also know that there's 3 negative electrons to balance the 3 positive protons. I know that the mass number is giving me a sum of 2 parts. If the mass number is 7 and 3 of those 7 units are taken by the protons, how many are left to be neutrons? If all the particles inside of the nucleus add to 7, and 3 of those particles are protons, the remaining 4 particles must be neutrons, because 4 plus 3 gives me 7. In this example, the standard isotopic notation for carbon: protons, neutrons, and electrons. How many of each? Since the atomic number was 6, atomic number actually is 1T, let me correct that. I know with confidence that the number of protons is 6. By definition, the atomic number gives me the identity of the atom. And therefore, I also know that there's 6 electrons because atoms are neutral. The positive protons must be electrically balanced by the 6 electrons. And if the total mass of the carbon atom weighs 12, and 6 of those 12 units have already been accounted for by the number of protons, the remaining particles contributing to the weight must tell us that there's also 6 neutrons. So between the mass number and atomic number, we can easily find how many of each particle there are. So this is some molecular art as well. What would be the standard isotopic notation for the following molecule? Well, these positive charges gives us the identity of the atom. Do you notice that there are 2 positive charges, which tells us that there's 2 protons? Those 2 protons gives us the atom's identity. Protons gives us the atomic number. Well, who's number 2 on the periodic table? Who is number 2? Well, that's going to be helium. I'm trying to find my chart. Here it is. Yep, number 2 is helium. So I can tell you that helium with the elemental symbol He is the identity. I know that a subscript to the left will give us the identity of the atomic number. And the top number is the mass number. And that's found by adding the neutral neutrons to the positive protons. How many total particles? 1, 2, 3, 4. The standard isotopic notation of helium, 4/2. The total nucleus has 4 components. 2 of the 4 are protons. Helium, 4/2. That's not so bad. An element has 9 protons. Okay, well right there we already know who it is, because 9 protons gives us the identity of the atom. The atomic number equal 9. Who is that? Oh, number 9 on the periodic table is fluorine. So I can think about fluorine with its elemental symbol F, and as a subscript to the left, a number 9. I got all of that information for the first few words. An element has 9 protons. It also has 10 neutrons. So think about what we just drew in that picture before. We have 9 positive particles. 7, 8, 9. 9 positive protons. And we have neutrals, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I know they're supposed to be mixed around, not just ordered stacked. So there's 10 neutrons. And I put in 9 positive protons. How much does that nucleus weigh? So the particles add together. If I said we had 9 positive protons and 10 neutral neutrons, the mass number, the total number of particles in the nucleus is 19, and the mass number goes as a superscript to the left of the number. We said there was 9 positive protons And because atoms are neutral, that would give us 9 electrons as well. The atomic number is 9, and we've identified the element to be fluorine. Pretty simple with practice. Let's try another together. Identify the element that has an atomic number of 19. Okay, pause. Pull out the chart and find number 19. When I find 19, I find the elemental symbol potassium. Give the number of protons and electrons in the neutral atom. Well, that's easy. The identity of the atom told us there were 19 protons, and because electrons have to match the protons, we also know that there's 19. We do not know the mass number. And I'll clarify because it gave us no information about neutrons. And we'll introduce that a little bit when we talk more about isotopes. So that's all the information this particular problem could pull out just by knowing the atomic number. Without knowing mass number, we have no information about the neutrons, so we're going to leave that off. Try one on your own. Pause me. Tell me what elemental symbol we have in standard isotopic notation. You ready to try? All right, so the blue represents protons and the oranges represent neutrons. Let's count. I have 1, 2, 3, 4, 5, 6 positive protons. And I have 1, 2, 3, 4, 5, 6, 7 neutral neutrons. The identity of the atom comes from the number of protons. That's the identity from the atomic number. And we also know it represents then, of course, the number of electrons because atoms are neutral. Who's number 6 on the periodic table? That's carbon, isn't it? The atomic number goes as a subscript to the left. The sum of all the particles in the nucleus, all of the protons and neutrons, well, there's 13 particles. So this standard isotopic notation is an isotope of the most abundant carbon, which is 12, but this happens to be carbon 13 with 13 total particles in its nucleus. So 13 over 6 in the elemental unit of carbon. You had a next picture to try that same skill with. We had 1, 2, 3, 4 positive protons. That's your atomic number, which also gives you electrons since it's a neutral atom. 4 positive protons, number 4, well, that's beryllium, Be. The atomic number goes to the left as a subscript. How many total particles? Well, here's 1, 2, 3, 4, 5 neutral neutrons for a total of 9 particles in that nucleus. So 9 over 4, Be for the element beryllium. Let's keep practicing on page 7. How many protons, neutrons, and electrons are contained in each atom given the atomic number and mass number? Well, let me model letter A, ask you to pause and do letter B and C in the similar fashion. Notice that Z is what we refer to as atomic number. And the letter A is what we refer to as the mass number. So any element, let's just use a generic symbol, X, places the mass number over the atomic number. Alrighty, so with that in mind, the Z, which is the atomic number, is 17. The mass number is up high as 35. How can we derive the elemental symbol from that information? Well, I use the periodic table and find element number 17. Number 17 is the element chlorine, Cl. By definition, atomic number gives me the number of protons and electrons because atoms are neutral. So I have 17 positive protons. I have 17 negative electrons. And if I have a total of 35 particles, and of the 35, 17 have already been accounted for as protons, the remaining mass must be coming from neutral neutrons. So I'm subtracting the large from the small number, large minus small, and I can get 18 neutral neutrons for letter A. Try B and C and come back when ready to check. Don't cheat yourself, please. Okay, welcome back. I'll keep talking. Letter B. I have a mass number of 28 set over 14. Notice that we always put the large over small number. I go to my periodic table and find number 14. It's the element silicon, elemental symbol Si. I know that there's 14 positive protons based on the definition of atomic number. And I know since atoms are neutral, there must be 14 negative electrons. And 28 minus 14 is 14 neutral neutrons. Remember that 28 minus 14 is how I found the neutral neutrons. Here's the total mass minus the protons. 28 total particles, 14 of the 28 have been accounted for already as protons. The remaining mass must be neutrons. Letter C. The large number is 238, mass number. The smaller number is 92, the atomic number. Who's number 92? Well, that's uranium, capital U. By definition, the atomic number tells me 92 protons and 92 electrons because atoms are neutral. 238 minus 92 is 6 for 146 neutral neutrons. The total mass, 238, of that 92 of those were already accounted for as protons, leaving the remainder to be the neutron number. The next part, the very bottom of your notepad page, let's check those two while you're here. What's the mass number of an atom? And if it contains 42 protons, 42 electrons, and 53 neutrons, remember that mass number is the sum of protons and neutrons, and those little electrons are just fleas on a dog. They do not contribute to the weight. And so I'm going to add 42 protons to 53 neutrons. I'll add 24 protons to 28 neutrons. That will give me the mass number. So I'm going to have to give myself a little more room down here. Letter A, 42 protons plus 53 neutrons gives me a mass number of 95. Protons, neutrons. So I can take that into standard isotopic notation. Who's number 42 on our periodic table? Number 42 gives me the identity as molybdenum, a mass number of 95 over atomic number 42. And letter B, doing such good work. We have 24 positive protons added to 28 neutral neutrons. It's 12 carry the 1. So that's 52 total units as a mass number. Whose element number number 24? Oh, that's chromium, isn't it? The elemental symbol for chromium, where the total mass is 52, set over atomic number of 24. There's its standard isotopic notation based on the information provided from protons and neutrons. Let's pause our video here, and we'll come back to talk about specific isotopes. We'll actually need our calculator in the next lesson as well. I'm so proud of your hard work in our first lesson today.